Atomic structure is topic 2 of the IB syllabus, and it's going to be our second unit as well. So a lot of these basics you guys have heard before, and I'm just going to do a really quick overview of them. When you think of an atom, you probably know that it's composed of smaller fundamental particles, what we can call subatomic particles or fundamental particles. Those are protons, neutrons, and electrons. So just a simplified overview of those things. The protons and the neutrons are both in the nucleus. That's their location. Sometimes they're referred to as nucleons because they're both in the nucleus, whereas the electrons are outside the nucleus. Exactly where those electrons are is a little bit trickier to pinpoint, a lot trickier than maybe you've covered in the past, but we will eventually get to the idea that they are in energy levels. Those energy levels are a bit complicated, but that'll be part of our later discussion of atomic structure. For now, we know protons and neutrons are in the nucleus, and electrons are outside the nucleus. Protons have a 1 plus charge, and right like that, +1 charge. Neutrons have 0 charge, and electrons have a -1 charge. Okay? And atoms are neutral, meaning they always have the same number of protons and electrons so long as they are still considered atoms. In terms of mass, a proton can be considered to weigh 1 AMU, or 1 atomic mass unit. So it just means, like, relatively speaking, a proton weighs 1, or it weighs about 1/12 as much as carbon-12 does. A neutron also weighs 1 AMU. They're very close in mass, almost identical. And an electron, we're going to essentially say, weighs 0. An electron weighs 1 out of 1,837. It would take 1,837 electrons to add up to the mass of a proton. So in that sense, it basically doesn't matter because you're never going to have 1,837 electrons. The biggest atom that's ever been even made has 118. So not even close, by a factor of 10. So we just ignore it and say that electrons have basically no mass. This is the table in the data booklet that discusses these topics. So it gives you masses and charges. It uses more like actual SI units. So the values obviously are really tiny, -27. This is in kilograms. But you can see that the proton and the neutron are almost the same, the neutron being a tiny bit heavier, and the electrons are a factor of, 1,000 to 10,000 times smaller. In terms of charge, you can see protons and electrons have the exact same charge, but that's the amount of charge, and then they have an opposite sign, whereas the neutron has no charge. So a very common question type is to give you a chemical symbol, and the chemical symbol may include atomic number, it may include mass number, it also may include charge. And from that symbol, you should be able to determine the number of protons, neutrons, and electrons, or you should be able to determine the charge, or you should be able to determine the mass number. Okay, so from this picture, this big X represents any chemical symbol for an element. When you have a chemical symbol, that's what is listed on the periodic table. The first letter is always a capital letter, and if there's more than one letter, the second letter is lowercase. The atomic number either gets listed down at the bottom left, or it doesn't get listed at all, and you're expected to look it up on the periodic table. So for this one, you can look up on the table. Okay. Important to note. And the mass number gets written, when you talk in this chemical symbol notation, the mass number gets written at the top left. So the mass number equals the number of nucleons in the nucleus. So before I said a nucleon is a proton or a neutron. So the mass number, another way to think of it, is the number of protons plus the number of neutrons. Okay. So determining the number of neutrons, if the atomic number is the number of protons, and the mass number is the number of protons plus neutrons, if we subtract the two, if we find the difference, we'll know the number of neutrons. So all you have to do is take the mass number minus the atomic number, and you get the number of neutrons. Right? Again, mass number is protons plus neutrons. This is protons, so if you subtract them, you're left with the number of neutrons in an atom's nucleus. Okay? I don't know why I have this written twice. Determining the number of neutrons is mass number. I'll subtract this thing out. We don't need that. Okay, the charge. So this is based on the balance of protons and electrons. This tends to trip some people up because when atoms obtain a charge, they turn into ions. Okay? So ions are atoms that have gained or lost electrons and therefore have an overall charge. Okay? Or those are monatomic ions anyways. We'll get to polyatomic ions later. But for now, if an atom gains or loses electrons, it gets an overall charge. Atoms are not going to gain or lose protons. So protons are not lost or gained. In any sort of simple chemical process that we're looking at, the protons remain the same. Okay, so if the protons are remaining the same, it's only electrons being gained or lost. So when you're doing charge, when you lose electrons, you are losing a negative value. So it's like subtracting a negative, and the charge becomes positive. Okay. Gaining electrons, the charge becomes negative because it's like adding a negative number. So we'll do some practice with that. But it's all about the balance. How many extra electrons or how many extra protons do you have? Okay. And so the number of electrons can be determined by looking at the charge. We'll do some practice. There's something to watch out for. This is chemical symbol notation, what you would use in a problem where they said, determine the number of neutrons. This 56 up here is the mass number. Okay. But this is not what's listed on the periodic table. On the periodic table, you get something that looks more like this. You get a big 26, a whole number, and then you get a 55.85. Okay? It's important to point out that number at the bottom is something called the relative atomic mass. Not the same thing as the mass number. You notice it's close to the mass number given here, but they're not the same thing. We'll clarify them shortly. And this number up here is the atomic number. So oftentimes in questions dealing with these chemical symbols, figuring out the number of neutrons, protons, electrons, all they're going to give you is this. And so if you want to calculate the number of neutrons on this symbol, this Fe56, you have to take the initiative and look at the periodic table and figure out, okay, there are 26 protons. So if you're trying to do the math, you get your mass number equals 56. You look at the periodic table and get atomic number equals 26. And if you subtract them, you get the number of neutrons equals 30. Okay? But notice they don't give you the 26. So you've got to go and look that up on the periodic table. Also quickly, this letter Z, as odd as it may seem, this letter Z is going to be important that you recognize that represents atomic number. It sort of represents the positive charge of the nucleus. Okay, so sometimes they'll use that symbol Z. Okay, let's do a practice problem or two just to see how this all plays out. So sulfur. Sulfur written with 32 on the upper left. Remember that this 32 is the mass number. Okay, it's not the atomic number. If you want to do the atomic number, you look at the periodic table, and sulfur is atomic number 16. Okay? So you always are going to have to go take that step on your own, look at the periodic table. Atomic number 16, that means there's 16 protons. So if something gets the symbol S, it is sulfur. It is atomic number 16, which means it has 16 protons. That cannot change if it's still going to be sulfur. The minute you make this proton number different, it becomes a different element and it gets a different symbol. On this symbol, there's no charge written in. The charge would be written at the top right, as it is over in this example. So sulfur has no charge. If it has no charge, then the protons and electrons are the same. Then they must be balanced. And in this example, if the mass number is 32, 32 minus the atomic number means that there must be 16 neutrons, okay? Because 16 neutrons, 16 protons adds up to 32 for the mass number. I'm going to skip ahead and do one that has a charge. So this one's copper. If you look at the periodic table, copper is element 29. So you look at the periodic table, it's atomic number 29, and that gives you the answer here. It has 29 protons. That number is locked, okay? So when you're trying to figure out this plus charge, you don't add 2 more protons to the number of protons. The number for copper is 29. It has to be 29. You can't change it. So how do you get a 2 plus overall charge? Well, you must have lost 2 of these negative charge things. You lost 2 electrons. So between these two, there's now 2 extra protons, hence why you have the 2 plus charge. So this ion is formed by copper losing 2 electrons. And for the neutrons, you're subtracting 63 minus 29, and that gives you 34 as the number of neutrons. Okay. And this one on the right, given protons, electrons, and neutrons, you should be able to figure out the symbol that goes here. So I'll leave that for you to try to figure out and for us to talk about in class. Okay, on the periodic table, the mass number is not listed. So the only time when you're going to do a question on number of neutrons is when the mass number is given to you, as it is in these examples, this number at the top left. On the periodic table, the relative atomic mass is listed. And we already talked about why things are called relative atomic masses. It's because the mass is compared to each other. Down a little bit. Okay. So atomic masses were originally determined by elements being compared to each other, as we've already spoken about. Hydrogen, oxygen, carbon have all been used as the standard for the other masses, but now we know that carbon-12 is the standard. Everything else is compared relative to carbon-12, which is why they're called relative atomic masses. The idea is that one atom of carbon-12 equals exactly 12 in terms of mass, so exactly 12 atomic mass units. Or you can think of it as one atomic mass unit is equal to 1/12 the mass of a carbon-12 atom. This is also the standard for Avogadro's number, for the mole number. The number of atoms in 12 grams of carbon-12 is 6.022 times 10 to the 23rd atoms. Okay, the other topic of this video is isotopes. Okay? So where do all these numbers come from on the periodic table that have these decimal places? Right? If you thought about mass numbers are always whole numbers because there's always a whole number of protons and neutrons. So then why are the masses on the table somewhere in between? Why are they decimals? Well, the reason is that there are these different versions of the elements. It's not a technical way to define it, but that's a way to think about it. So there are different versions of the elements, and the way to define an isotope is that they are atoms. You have to point out that they are atoms, so they don't have a charge, usually when we're referring to isotopes. So atoms with the same number of protons, but a different number of neutrons. Okay? You could also use, instead of number of protons, you could say atomic number, and you could say mass number. Okay? So, for example, hydrogen has 3 different isotopes it can exist at. The normal version of hydrogen, by far the most common version of hydrogen, is just hydrogen that has 1 proton in its nucleus and no neutrons. But there are 2 other forms of hydrogen that can exist where there's 1 neutron and 2 neutrons. So what changes is the mass number. Okay? In terms of properties, the only difference between isotopes really are physical properties. So those physical properties don't have to do with how it reacts. They have to do with other properties. So they have different masses. This usually isn't really accepted as a property on the IB exam, though. Better to point out that they would therefore have different densities. And this can sometimes affect their boiling points. But I'd say the easiest one to remember is that because they have different masses, that will affect how dense samples of different isotopes are. Okay, but they have identical chemical properties. So props means that all isotopes react in the same way to each other. And then you have carbon, carbon-12, carbon-13, carbon-14. All of these exist in our atmosphere and on the planet. Carbon-12 is by far the most abundant and it's the most stable. But there are these 3 different kinds of carbon. This is showing the carbon nucleus, and you've got 6 and 6 protons and neutrons to add up to 12, the mass number. carbon-13, 6 and 7, and carbon-14, 6 and 8. So they all have 6 protons, they all have 6 electrons, so their chemistry is the same, the way they react is the same, but they have a different number of neutrons, which gives them different mass numbers, different masses, different densities. Okay, and so when you see on the periodic table those values with decimal places, that is a relative atomic mass. It's an average atomic mass. It's a weighted average of the masses of all the isotopes of an element based on their abundance and compared to carbon-12. Okay, so these percentages, they matter, and the actual mass of carbon on the periodic table is 12.01. So because it's 99% carbon-12, it's the average mass of a carbon atom is very close to 12, but these heavier isotopes do pull the average up slightly above 12. Not very significant in carbon's case, but it is more significant in other elements' cases. So a very common question type is to have you calculate the average atomic mass of something, the relative atomic mass, given isotopes and their percent abundances. Okay, so I'm going to skip the non-calculator method. I'll talk about that in class. I'll do one problem and then we'll wrap up this video. So lithium. Lithium has 2 main isotopes, lithium-6 and lithium-7. Lithium is atomic number 3. So lithium-6 is 3 protons, 3 neutrons. Lithium-7 is 3 protons, 4 neutrons. Lithium-7 is the much more abundant isotope. 92.41% of all lithium atoms on planet Earth are lithium-7. Okay, so that essentially what that means is if you scooped up lithium and you grabbed 100 atoms, about 92 of them would be lithium-7 and about 8 of them would be lithium-6. Okay? Now, if you want to do the calculation, you're doing an average, and you want to think of it sort of in those terms, like if you had 100 atoms. So one way to do this is to say, if I had 100 atoms, 7.59 of them would be ones that weigh 6. And 92.41 of them would weigh 7. And then since it's an average, I need to divide that whole thing by 100 because I'm talking about having 100 atoms. Well, if I do that, I get 6.92 as the average. You can see that that's a lot closer to 7 than it is to 6 because you have a lot higher percentage abundance of the 7 one than of the 6 one. A way to simplify the math a little bit, instead of using these whole number here and dividing by 100, you can turn the percentages into decimals. You can essentially divide by 100 ahead of time and make it 0.0759 times 6. So this is 7.59% as a decimal. And this is 7, and you will get the exact same value. Okay. So either one of these mathematical ways is correct. And this is the value that you would see on the periodic table. If we skip back here and we look at lithium, 6.94, our average value was 6.92. Okay, so not bad for quickly doing it with the numbers given. Okay, so we'll do more practice in class, but to recap, we've got fundamental particles inside of atoms. They've got different charges and masses in different locations. Given chemical symbols, we can calculate mass numbers, numbers of neutrons. Charges allow us to calculate number of electrons and vice versa. And then on the actual periodic table, we don't get mass numbers, we get relative atomic masses, which usually have these decimal places, and that's due to the presence of different isotopes, atoms with the same number of protons but different number of neutrons. And a very common question type is to be given the percent abundance of different isotopes and to have to calculate what the relative atomic mass is, what the average mass is based on 2, 3, or even 4 isotopes. Okay? And we will do some more practice with that in class.